Welcome back. We just defined the notion of reflexive Banach spaces, and those are those guys for which the canonical map is an isometric isomorphism. Few properties that we have to assemble now about reflexive Banach spaces. The first one is still written here. There's this proposition. We proved already the first part. So if you have reflexive Banach space, then closed subspaces have exactly the same property. And now what we will finish here up front is the second statement that if you have a reflexive Banach space, then any Banach space isomorphic to it is also going to be reflexive. This is a bit of a abstract thing. You have to play carefully around with all the definitions, and you have to invoke the dual transformation. That's important. So the first part we did here. Now the second part we started down there. So moving ahead, if you have two Banach spaces, first one X, suppose that's the one which is reflexive, and now you have a target space Z, and these are isomorphic. I have to show that Z is reflexive. That is to say, I have to pick an arbitrary element in the bidual of Z, and I have to show that it is in the range of the canonical map of Z. Okay, that's what reflexivity means. Okay, good. So now here's this map capital A that we will use. It's an isomorphism, and then we get started. So we first use the dual transformation of the dual transformation of A, because you need to apply it twice because you want to investigate the bidual spaces, right? So just having the dual there once, that's not going to cut it for you, so you have to have it twice. That's what is going on here. And you know this is also an isomorphism. Well, it's an exercise in our problems class, but that's easy. All right, and then we get started. So now take an arbitrary element in the bidual of Z and show that it is in the range of the canonical map of Z. All right, and the construction goes as follows. So you will understand why. You define element K, which is sort of the pullback of the L element in the bidual of Z to an element in the bidual of X. And why do you want to pull this back? Yeah, because you know that all these elements in the bidual of X, how they look like, because it's a reflexive space. That's why you do it. All right. So you have K. Now, as I said, since X is reflexive, there exists a vector such that this K is of this type. K is equal to J sub small x, and the action of J sub small x is just a pointwise evaluation on the functional that you use to evaluate it. All right. In turn, this element X allows us to define Z, which is the image of X under the map A, which is a point in Z, right? You need a point in Z to show that this is equal to some J of Z, right? Because this element here has to be in Z. All right. That's why I push it forward again. All right, good. And now we have to check. Now check that. So I have to take an arbitrary functional G in Z star. Yeah, but since my dual transformation is invertible, of course this here, okay, running out of space. This G I can always write as A transposed or dual of A inverse acting on F, okay, where F is a linear functional in X. This is because the map is invertible. For an arbitrary G, you can always find a unique F such that this equality holds true, because the dual transformation is invertible. Okay, so now starts the sort of, well, I guess algebra. So K, A transpose G. Okay. So by definition, let's use colors here. So we will have this equation that will be used right now, because if you bring the A transpose, the dual of A to the left, then you have that the dual acting on G is equal to F, so K acting on F. Fantastic. Now K acting on F, you know what this is because you work in a reflexive space. So by the green one, this is equal to JXF. All right, now you use the fundamental definition because F is in, so here maybe I should write this, F is a linear functional on X. And you know how that little J acts on linear functional on X. This is pointwise evaluation. So this is F of X. Okay, good. Now, what do we have? So this small f by the pink one again, is simply A transpose G acting on X. And now you need to remember the definition of the dual transformation. Dual, maybe trafo. Dual trafo. Dual trafo. Remember how this worked? So this was G of A of X. And well, A of X, okay, I'm kind of running out of colors here. So that red one now is A of X is equal to Z. So this is just G of Z. Okay, good. So that's one chain of equalities. Now we need a second one. And L of G. Okay, so where is L? Oh, yeah, no, it's up there. So I have to scroll all the way up. So this is the one with the yellow arrow. This one here, right? So this equation allows me to express L in terms of K, and I will have the dual transformation of the dual transformation acting on K. Okay, so let's, okay, hopefully I can do this by heart. So this is equal to A transposed K, and then all of that acting on G. Okay, so now I'm going to use again the definition of the dual trafo. So maybe let's write this here because I've used it now already twice. So in general, the dual transformation would go like this. Okay, if so, AT is a bounded linear transformation, say from well, here it's X and Z, right? So Z X star. And so this here means J is a linear functional in Z star, and yeah, that's it, right? And X is a point in X. Okay, sure. Now what you do is you apply this equality one level deeper. That is when you're not acting on the dual spaces, but on the bidual spaces, right? So in a sense now, what you should identify is what I underline here in green. So this green part will be, well, the dual of the dual, and then your G, maybe with a dot, is gonna be this element in the bidual, right? Because you're one star deeper in the rabbit hole, and then the point that you evaluate on is not a vector in X, but it is a or in Z, since we're here in Z, it is a linear functional, right? So that should clear what I'm doing now, should clarify what I'm doing, right? So then this is simply K, right? Because the green circle goes outside, and then inside I have, well, I erase one T. Okay, very good. And then I act on the G, right? That is it. Okay, so that requires some thought, but this is it. But now look what I've achieved. Okay, I'm kind of out of colors, maybe like this. So I have that L of G is equal to this guy. Yeah, but this guy is up here on the left and is equal here to this one, right? So I indeed have L of G is equal to G of Z. And that's precisely what I wanted. So we have L of G is equal to G of Z, and thus remember how that map little J acts. That's precisely pointwise evaluation at the point, exactly what's written here. Okay, and thus L is equal to J A X, which is J of Z. Okay. This shows that the canonical map on Z is also surjective, and hence, and thus Z reflexive. Okay? All right, that's the end of the proof. Very nice. Okay, so this, of course, this requires some study what I'm doing here, but it's careful execution of the definitions that we had: dual transformation, reflexivity, but dual transformation not just on the dual space but on the biduals, right? Good. All right, nice. Now next result, that's going to be a bit deeper, is the following theorem. A Banach space X is reflexive if and only if its dual space is reflexive or reflexive. Okay, dual space X star, let's give it a name, dual space X star is reflexive. Okay, that's the statement, right? So now, since we're talking about reflexivity of a dual space, by default we will have to work with triple duals, so 3 stars, right? Because reflexivity of a dual space means that the canonical map from X star to X triple star is surjective, right? Because dual space is again a Banach space, right? Good. All right, so let's start. Proof. So first I will write down what, reflexivity means. I just said it in words, but since this is all still very fresh, let's write it down. Reflexivity of the dual space is equivalent to the surjectivity of the map, of the canonical map. I will call it also J, but that's not the one from X to X double star, but for the one from X star to X, well, triple star. And triple star is just, well, the dual space of the bidual. I don't need to define this anymore. Okay, from the dual space X star to its bidual X triple star. So just X star and then 2 stars on top. Okay, so how does it act? That acts, well, it's kind of clear. That acts as, so now the ordinary canonical map, it maps a point in X to an element in the bidual. So what this thing does is it takes a functional and maps it to a point in the triple dual, right? So acts as, it takes something here, say F, and it maps it to J sub F. That's the kind of notation I use. I prefer to write F for the functionals and X for the ordinary vectors in the vector space. But again, that's just notation. In triple star. And what's the rule? Well, yeah, the rule. Well, let's use the elements in the bidual. Let's write the elements in the bidual with capital letters. So J small f on capital F is just pointwise evaluation of the element in the bidual on the functional in the dual. Okay, so this is this. All right. This is just the definition. That's just the definition. I haven't proven anything. In short, J surjective if and only if for every K in the triple dual there exists linear functional so that this K is just J sub small f, and the action of J sub small f is written up there in the yellow box. Okay, good. So that's preparation. Well, with, okay, apparently I write more in my notes. So with, just repetitive now, J of FF is equal to capital FF for every capital F in X double star. Okay, good. Now let's get started on proving something. This is all preparation. This is just spilling out the definition of reflexivity of the canonical map from the bidual to the triple dual. All right, good. Now suppose we will start by assuming X is reflexive and then proving that the dual space is reflexive. So now suppose that X is reflexive. Okay, and let k be an arbitrary element, be arbitrary. All right, now using the map, which is the canonical map now on X, so I can't call it J anymore, so I will call it I. So that guy goes from X to the bidual, and I'm not going to call that element in the bidual J sub X, but I sub X. So with X is sent to I of X, where IXF is just pointwise evaluation on the vector. For all F here, we define a map G, which is K composed with capital I. All right, so that is well defined because I takes a vector in X, assigns to it an element in the bidual, and then K, which acts on elements in the bidual and spits out a scalar, right? Because K is in the triple dual, right? So this is well defined. Okay, this is linear functional. Okay, and note that J is a linear functional. This is because composition of linear bounded things give you linear bounded things, right? Because K is bounded linear, I is bounded linear. So composition certainly is linear, and using simple norm estimate, you see that this is bounded. So this is a bounded linear functional. And how does it act on a vector? Well, G of X, this is easy, just copy paste the definition, is K evaluating at I of X for all X in X. Okay, nice. But since X is reflexive, that G, of course, every capital G in the bidual, every capital G in the bidual is of the form capital G as small I of X for some X in X. All right, so together, what have we got? We have that, yeah, I want to write it here because I want to use those definitions up there. So let's move this a little bit up here so that I have space. So K acting on capital G, right? So that is well defined because K is an element in the triple dual and G is in the bidual. So that is fine. KG, so that KG, okay, again, colors. Well, I will run out of them soon. So this is KIX. Then KIX is simply G of X because of green. It is G of X. And then G of X, the standard action of this fellow here on X is IX of G. And now IX of G by yellow is, it is G of G. Okay, I need to move that thing to the left. Here, I like this. G of G, and now capital G of G. Where is it written? Capital G of G. Oh yeah, this is by, okay, this is by the yellow box up there. So you have, instead of capital F, you have capital G, and instead of small f, you have small g. So that's precisely what's written up there, right, in the yellow box. So this is equal to yellow box, and this is equal to JG of G, all right? And this works for all elements capital G in the bidual of X, right? And now if you carefully read this equality again from just this here equal to this here. That's precisely what you wanted. If you read what I wrote upstairs about surjectivity of the canonical map on the dual space to the triple dual, right? That's precisely what we wanted to show. Okay, so this proves that J from the dual to the triple dual is surjective, and thus the dual space reflexive. Okay, good. Now the second part. So if we have a reflexive dual space, how do we conclude that the initial space X is reflexive? All right, so conversely, if the dual space is reflexive, well then, so is, by what we just showed, the dual of it is reflexive, right? We just proved, given a Banach space, then its dual is reflexive, right? So now I start with the Banach space, which is the dual itself, and then its dual, which is the bidual, is reflexive. That's what I just proved. Okay, conversely, if this is reflexive, then so is the bidual by the first part of the current proof. Okay, good. But range, now you finally need the completeness, but the range of the canonical map on X is closed, is a closed subspace, is a closed subspace of the bidual. Now remember that proposition right before that theorem. It was if you have a reflexive, Banach space and you have a closed subspace, then that thing is also reflexive. So here my closed subspace is gonna be the range of J, right? And since the bidual, which is a subspace in the bidual, and the bidual is reflexive, then so is the range by that proposition, all right? It's a closed subspace, and thus reflexive by the last proposition. Okay, hence, given that X and range of J are isomorphic, why are they isomorphic? Well, the simple fact is, if you take the map J, so it's not far from an isomorphism in general. The only thing that can fail is the surjectivity, right? Because it's injective, it's an isometry in any normed linear space, but it might not be onto. Yeah, but how you can surely make it onto is you just take the domain equal its range. Then, of course, trivially it is onto, right? So, and that map now is an isomorphism between those two Banach spaces, okay? So they are isomorphic. Yeah, but you know that the range is reflexive. So now you again use the proposition that if you have two Banach spaces, one of them is reflexive, and these Banach spaces are isomorphic, then the other one is also reflexive. So by that result, since the range is reflexive, X has to be reflexive, okay? Given that are isomorphic, it follows that X is reflexive by the last proposition. So we used it twice. That's why we needed that thing up front. Okay, and that's it. That's the end of this result. Good. All right, so this is very important stuff right now. Now, having this very important stuff, you can now prove for yourself that if you have a reflexive Banach space, if you're in a reflexive Banach space, and if it is separable, then the dual space is separable. Think about it. Maybe I will put it on the exercises, but now you have enough tools to prove that. Right, for the other direction, you don't need any reflexivity. That just works. We proved it before we discussed any of this dual stuff. but for this one you need reflexive Banach space. Okay. All right, good. So now what we will do is we will compute several dual spaces and ask ourselves, you know, which kind of spaces are reflexive and which are not. And this is not so straightforward. It requires a bit of trickery, but we will do it. So I will state the first one. We won't be proving it in this video because we're almost out of time, but nevertheless I will state the claim. So in Hilbert space, let H be an arbitrary Hilbert space. Then first, what about the dual space? Well, it's not equal to its dual space, but the next best thing, it's isomorphic to its own dual space. Okay. H star, and moreover H is reflexive. Alright, so if you only work with Hilbert spaces, then you have no need for this concept of reflexivity because they are always reflexive. Okay. So this will be the first thing that we will prove. It is because of Riesz representation theorem, because that's why it's so powerful, because it really captures all linear functional as inner products of, you know, with some, you know, special vector there, and that's why dual spaces and Hilbert spaces are so simple, at least from this viewpoint. Once you're out of the Hilbert space, once you don't have that geometry, aka the inner product, things get more complicated, and then results won't be as pretty as this one anymore, but this we will all do in the next video. Okay, see you then.